This is your presenter, Asloob Mudassar, and I am presenting slide number 18B of the course on atomic and molecular physics. In the today's lecture, I shall be covering the following topics: molecular orbitals and LCAO approximation. LCAO stands for linear combination of atomic orbitals. The second is binding energy in the ground state of hydrogen molecular ion. And this lecture is the second lecture of the series on molecular physics and is in continuation of the previous lecture which was given in 18A. Molecular orbitals and LCAO approximation. So once again, LCAO stands for linear combination of atomic orbitals. Hydrogen singly ionized molecule. This molecule will be discussed in the today's lecture. H2 molecule. H2 singly ionized molecule can be treated exactly. Exactly mean that its analytical solution is possible. And we can have direct and exact equations, mathematical equations, and we can infer information from those equations. That is why I have said that H2 singly ionized molecule can be treated exactly. There are some important approximation methods, the results of which can be compared with exact methods. So you see that I shall be in the following lectures, in the following pages, I shall be presenting some other techniques which can be compared with the exact method. The advantages and deficiencies of these methods are then revealed. So you see that I shall compare different methods with the exact methods and their advantages, their merits and demerits, and their deficiencies will be revealed in the comparison. These methods can then be applied to larger molecules where the exact treatment is not possible. So you see that this is the simplest molecule of its kind, H2 singly ionized molecule. And when we shall be dealing with heavier molecules or with larger molecules, then of course those larger molecules can be their informations can be based on the exact treatment which comes from the H2 molecule and from the other methods which are approximate methods. So many other methods will be discussed with the exact method of the H2 singly ionized molecule, and some informations will be derived that how these other techniques can be made very close to the exact method. So following similar methods, we can treat larger molecules, and the approximate methods can be similarly refined in a way to give results close to the exact method. And remember that the exact method is not available for larger molecules. In LCAO, which is a linear combination of atomic orbitals, in the LCAO method, molecular wave function is composed of linear combinations of atomic orbitals of the atoms that form the molecule. So you see that it is very simple that we need to consider the linear combination of different atomic models which formulate the molecule. Coefficients in the linear combination are optimized in such a way that the energy calculated with this molecular wave function becomes minimum. So you see that when you have a linear combination of different atomic orbitals which form the molecule, then of course coefficients are present. And we shall optimize our wave functions in such a way that the wave function will give you the minimum will give you the minimum in the presence of different coefficients. So we shall optimize those coefficients in order to give you the wave functions which becomes minimum. The wave function obtained through optimization should yield lower energy than the energies generated by the approximate function. So you see that here I have said that the wave function obtained through optimization of these coefficients. So when you optimize the coefficients, which are the coefficients with the different atomic orbitals that form the molecule, and we optimize those coefficients, the wave function obtained through optimization should yield lower energy than the energies generated by the approximate functions. So through optimization, we shall have the wave function that would give you the minimum energy in comparison with the other approximate functions that we can suggest as a solution of the molecule, of the molecular wave function. So phi of x, y, z and its mod square. So this is the mod square of phi of x, y, z gives a spatial probability density distribution of the electron, which has molecular orbitals of the electron as a classical counterpart. You know that in classical physics, the electrons will have molecular orbitals. The spatial probability density distribution of these molecular orbitals will be given by the absolute square of phi of x, y, and z. Molecular wave functions are also called molecular orbitals. So you see that over here, the main process is to construct the molecular wave function of different molecules that we shall be discussing. So when the wave function is available, of course, then we shall be able to get different informations about the molecule. And the molecular wave functions will also be called as molecular orbitals. So you see that here I have the H2 singly ionized molecule on the left hand side, which can be considered to be consisting of the atomic hydrogen plus the singly ionized hydrogen. So here we have on the right hand side we have the hydrogen atom plus hydrogen ionized atom, that is a singly ionized hydrogen atom. So these two together will form the H2 singly ionized molecule. Hydrogen atom is the atomic hydrogen. So H is the atomic hydrogen in the state 1s. This H, which is on the right hand side of this equation, this is the hydrogen atom in state 1s, that is in the ground state. And H2 singly ionized molecule will be in its lowest energy state, provided this hydrogen atom, atomic hydrogen on the right hand side is in its ground state, and the other hydrogen atom which is also in the ground state, that is the H plus or singly ionized hydrogen atom, was also in the ground state, and we have ionized that electron, so we are left only with the proton. And you see that this is the condition that we are going to construct graphically. This equation, H2 singly ionized molecule, can be constructed as H plus H star, H plus sign, or H ionized plus H neutral hydrogen atom in both ways, which is depicted in the figure below. So I am going to discuss two possibilities. One possibility is shown on the left hand side. You can see that you have proton A, you have a proton B, that is nucleus A and nucleus B of the hydrogen atom. And here in this picture, nucleus A is connected, that is the electron is connected with the nucleus A. So nucleus A and this electron will form the neutral hydrogen atom, which is shown at the bottom as H. And the two nuclei are separated by a distance r. And the B molecule and the B proton will be referred to as H plus, that is H singly ionized because it has no electron. The other possibility is that you have A as a single proton with no electron associated or connected with it, and the B proton, and the proton shown in B or the nucleus B has an electron E connected with it through the distance RB. And you know that I have in the left figure, I have shown RA is the distance of the electron from the nucleus A. And on the right hand side, I have the figure in which the electron is connected or is at a distance RB from the nucleus B. And you know that for the left hand side molecule, I can write it as H plus H positive sign as a superscript. And on the right hand side, I can write a nucleus A as H with positive sign, that is ionized hydrogen atom, plus B with the electron can be written as a hydrogen atom, because it has the nucleus and the electron connected with that one. So equivalence of the two configurations, that is H plus H positive sign. For example, here in the left figure, the nucleus A is with the electron is the hydrogen atom, atomic hydrogen atom, and the nucleus B is since ionized, I have written as H positive sign. And on the right hand side, the nucleus A will be referred to as H positive, H ionized, whereas the nucleus B along with its electron will be referred to as the hydrogen atom, represented by the nucleus B along with the inclusion of electron. So you see that these are the two possibilities that I have shown in connection with this equation. So on the right hand side, you can write H plus H ionized, or you can write H ionized and H. And graphically, I have shown their representation. That is, either the electron is connected with the nucleus A, or the electron is connected with the nucleus B. The atomic orbitals of the electron in the hydrogen atom has the wave function given by. So you see that we can write down the atomic orbitals of the electron in the hydrogen atom. This is a hydrogen atom where we have the electron connected to the nucleus. So for such a hydrogen atom, the atomic orbital is given by equation number 18.27. So phi A as a function of Ra is equal to 1 over square root of a pi into A naught cube. And then outside of this one, we have a quantity e to the power minus Ra over A naught, where A naught is the Bohr atomic radius. The electron is either with A or with B. As we have discussed earlier, both possibilities yield the H2 singly ionized molecule, as shown in the figure above. The molecular orbital should be a linear combination of the electron being with A or with B. That is, so you see that here I am writing down the total wave function of the problem with a superposition or with a linear combination of two possibilities. That is, either the electron is connected with A or connected with B. So molecular orbital should be a linear combination of the electron being with A or being with B. That is, so on the left hand side, I have phi of R comma capital R is equal to C1 into phi A of RA plus C2 into phi B of RB, where phi A of RA is defined by equation number 27. We can write down a similar equation for phi B. And you know that C1 and C2 are the coefficients of this linear combination. And you know that Fa is the atomic orbital. Similarly, Fb represents the wave function corresponding to the atomic orbital B. And here, equation number 28 gives you a linear combination of these two atomic orbitals. And on the left hand side, we have capital phi, which is the molecular orbital. And this molecular orbital on the left hand side is actually represented by a linear combination of the atomic orbitals. So that's why it is called a LCAO technique, in which you have a linear combination of atomic models, atomic orbitals on the left hand side of equation number 28. Now you see that this Ra is equal to R plus R by 2. This equation is what I have written in the previous lecture, that is in the lecture number 18a. And I have also written there Rb is equal to R minus capital R over 2, where capital R is the separation between the two nuclei, and this small r is actually the distance of the electron from the center of mass. Capital R is the nuclear separation, and R, which is equal to the magnitude of the R vector, is a distance of the electron from the center of mass. The normalization condition gives, you see that we have to normalize each time we write a wave function. We try to normalize the wave function so that the probability given by the wave function that the electron is located in a certain region of space is equal to unity. So in order to calculate the normalization condition, we need to calculate the absolute square of phi. And you know that the absolute square of phi is given by phi multiplied by its complex conjugate. So I have on the left hand side of this equation, I have phi of R comma capital R and phi star of R comma capital R is equal to, so I have written down the right hand side of equation number 18.28 over here. That is phi of R comma R has been replaced by its value from equation number 28, and then I have also written phi star, which is also given from equation number 28. Now you can multiply these two equations simply on the right hand side, and you have C1 square into the absolute square of phi A plus C2 square into the absolute square of phi B plus C1 C2 into phi A and phi B star plus C1 C2 into phi A star and phi B. And you know that we can write the first two terms exactly in the same way as written above, and the last two terms can be combined together to give you 2C1 into C2 into phi A into phi B. Now you can take the integration of both sides of this equation over the allowed space, and then integral of a phi, and you know that phi into phi star is equal to phi absolute square or phi mod square multiplied by dr, because we are going to integrate over the given space, and the probability will be equal to 1. And on the right hand side I have C1 square, the integral of absolute square of phi a with respect to dr a, and then I have C2 square, and then the integral is over the absolute square of phi b multiplied by drb. And then the third integral is plus 2c1 c2 into the integral of phi a phi b into d cube r. So you see that I have written equation number 1831 in terms of the probability that the total function, that the probability on the left hand side given by the phi mod square is equal to 1. Integration is performed over the coordinate r of the electron, and you know that this absolute square of a phi a mod square with respect to dra will be equal to unity, so I have replaced it with the unity. And also the integral of a phi b mod square with respect to drb is also unity, so I have written unity with it one. But you know that this integral, which is equal to integral of a phi a into phi b with respect to d cube r, has been represented by SAB. So in equation 18.31 reduces to C1 square plus C2 square plus 2 times C1 C2 into SAB is equal to 1. The symmetry arguments given in the previous figure imply that C1 mod square is equal to C2 mod square is equal to C mod square, because the probability will be equal as mentioned in the previous diagram. So either the electron is associated with A or with B, both have the same chances, and their coefficients will also be related to with each other because they will be identical. The situations when the electron is with nucleus A or the electrons with the nucleus B, the situations are identical. So we have C1 square is equal to C2 square, and these two common can be set equal to C mod square. And this SAS with the subscript AB as shown in equation number 32 is actually the integral. SAB is the integral of a phi A of RA into phi B of RB into d tau. SAB depends on the spatial overlap of two atomic wave functions called overlap integrals. You know that when we defined SAB, it is a product of the wave function phi A and phi B. That is, it is the integral is the overlap integral of the two atomic wave functions. So it is called overlap integral. If the two nuclei are very far away from each other and there is no overlapping, then SAB, the integral represented by SAB, will be equal to 0. But when the nuclei approach to each other, as in case of a molecule, the two nuclei that is nucleus A and nucleus B, are not further away from each other, but they are in the close vicinity, and of course their atomic orbitals will significantly overlap, and that is why it is called an overlap integral. Molecular wave functions has either to be symmetric or antisymmetric with respect to the exchange of two atomic orbitals. And the exchange of two orbitals mean equivalent to the exchange of electron between nucleus A and nucleus B. So in such case, we can have the molecular wave function as symmetric wave function or antisymmetric wave function. And this demands that C1 is equal to plus minus C2. You know that here in equation number 33, we have the absolute square of C1 absolute square and then absolute square of C2. But you know that if you take the square root of both sides of this equation, then of course you will get C1 plus minus C2. C1 plus minus C2. So when C is equal to plus times C2, the resultant wave function will be symmetric, and when C1 is equal to minus times C2, the resultant wave function will be antisymmetric. So you see that substituting the value of C1 and C2, that is replacing C2 is equal to either plus times C1 or minus times C2, or you can represent these two constants C1 and C2 in terms of the constant given on the rightmost side of equation number 33, that is the constant C. So in terms of that constant, you can write C square is equal to 1 over 2 plus 2 times SAB. You know that this C1 and C2 can be substituted in the wave function which is given over here. For example, here we defined the wave function over here. You can substitute C1 and C2 in terms of these C constant, and then of course you can write the symmetric wave function and the antisymmetric wave function. And this constant through the normalization process will be given as C square is equal to 1 over 2 times 1 over 2 plus 2 times SAB. And the square root of this one will give you C is equal to 1 over square root of 2 plus 2 times SAB. The other value of C will be equal to 1 over square root of 2 minus 2 SB. Because of the symmetric wave function and because of the non-antisymmetric wave function using the plus sign and the minus sign, I have this C, which is 1 over square root of 2 plus 2 times SAB is for the symmetric wave function, which will be represented by phi S. And the other value of C, which is equal to 1 over 2 square root of 2 minus 2 times SB, is for anti-symmetric wave function represented by phi A. So you see that using the value of C in the previous equation, where we have defined the molecular wave function. For example, in equation number 28, you can put the values of C1 and C2, and you can have either symmetric wave function or anti-symmetric wave function, which are given over here. So phi S symmetric wave function is equal to 1 over square root of 2 plus 2 times SB, and then within the parentheses I have phi A plus phi B. And the antisymmetric wave function is equal to 1 over square root of 2 minus 2 times of SB, and within the parentheses I have phi A minus phi B. So equation number 35 will give you an expression for the symmetric wave function, and equation number 36 gives you the expression for the anti-symmetric wave function. Now you see that here through graphical representation, I am going to define or give you the picture or give you an idea of the symmetric and anti-symmetric wave functions. Plots of two wave functions and their absolute squared values are shown in the figure below. Here in part number A, I have shown the plot of two wave functions. Phi S represented with the red curve and phi A represented by the black curve. So you can see that the red curve represents the symmetric wave function because it is symmetric about the center, and the other wave function which is shown in black and represented by phi A is an anti-symmetric wave function. that is the positive values on the left hand side of this central point will be multiplied by the negative sign to obtain the right hand portion of that wave function. Now you see that in the bottom I am going to represent the absolute square of these quantities. So if you take the absolute square of phi s, that is the absolute square of phi s, it is again shown with a red curve, and you know that it is symmetric about the center. And if you take the absolute square of phi a represented by a dark curve, represented by the black curve, you will see that this black curve will also appear symmetric when I take the absolute square of phi a. The phi a is not symmetric, that is, it is an anti-symmetric. But if you take the absolute square of phi a, it becomes a relatively symmetric wave function. But you know that the magnitude in the center for the phi s absolute square is greater than the value of the phi a absolute square in the center when you compare the centers of both these functions. That is in the middle between the molecule, the value of the phi s symmetric wave function, its probability, that is phi s square, phi s mod square, is much higher than when it is in the anti-symmetric wave function. That is when we have the phi a mod square. So this phi s mod square is greater in the center as compared with its anti-symmetric wave function counterpart. And you know that these plots have been obtained by cutting through the surfaces with the cylindrical symmetry. So in the A, you have phi s, wave function phi s, and anti-symmetric wave function phi a. And in the B part, I have absolute square of phi s plotted, and I have also plotted the absolute square of phi a. So you see that I hope through this representation, the meaning of the symmetric wave function and the anti-symmetric wave function and their absolute values will be clear. The expectation value for energy, because you know that in quantum mechanics you normally calculate the expectation value of energy, which is given by this expression. That is on the left hand side I have written E average, which will be read as the expectation value of E, and on the right hand side I have defined it in the form of an integral, and phi s is the molecular phi is the molecular wave function, and here in the center I have the Hamiltonian. So phi Hamiltonian, then phi, and then integration with respect to d tau. So you can put it phi hat over here, more phi h hat more precisely over here in equation number 37, where h hat has been defined in equation number 38. So h hat is equal to minus h bar square over 2m, where small m is the mass of the electron multiplied by the del E square, which is the del operator keeping an information about the electron, and it is the function of r, where r is the position vector of the electron with respect to the center of mass, and then I have the potential energy term, which is minus E square over 4 pi epsilon naught into 1 over, within the parentheses I have 1 over RA plus 1 over RB minus 1 over R. This H or H hat is the Hamiltonian. For this one, you can see equation number 18.10, which was given in the previous lecture. So H is the Hamiltonian of the Schrödinger equation of the rigid molecule, which is given below. So this is for the rigid molecule. And you know that the rigid molecule is what I have defined in the previous lecture, where the two nuclei are clamped at a fixed distance capital R. So since this wave function phi has two possibilities, that it could be an symmetric function or it could be an anti-symmetric function. So I have written two Schrödinger wave equations given in equation number 40 and 41 with the corresponding eigenvalues as Es and Ea. And the wave functions, the symmetric wave function is phi s and anti-symmetric wave function is phi a, which we have already defined earlier. And these eigenvalues corresponding to the symmetric function Es as a function of R is equal to capital HAA plus capital HAB divided by 1 plus SAB. And for the antisymmetric wave function, the eigenenergy EA or as a function of capital R is equal to H capital HAA minus capital HAB over 1 minus SAB. So you see that here what is SAB? SAB is an overlap integral, and I have defined it earlier. Now I am going to define HAA HAB. The integrals HAA, HAB, SAB depend on R and are defined below. HAA is equal to defined by integral of phi A Hamiltonian operator, then phi A and integration with respect to d tau E. And HAB is equal to integral of phi A Hamiltonian operator, then phi B, and the integration is with respect to d tau E. And HBB is equal to the integral of phi B Hamiltonian and then phi B and d tau E. And SAA is equal to integral of phi A phi B. Here it is S, not AA, but it is SAB is equal to integral of phi A into phi B, and integration is with respect to d tau E, where d tau E under the cylindrical coordinate system is equal to r square into sine theta dr d theta d phi. And you know that in the first lecture I have already defined r, I have defined theta, I have defined phi there. And you know that RA is the distance between the electron and the nucleus A, and RB is the distance between the electron and the nucleus B. That is, RA and RB depend or measured from two different centers. That is, RA is measured from the nucleus A, RB is measured from the nucleus B. So these two quantities RA and RB are measured from different centers. The evaluation of these integrals over the electron coordinate require that both RA and RB must be measured from a common origin using a common coordinate system. So it means that we can represent RA and RB not in terms of the vector, in terms of parameter R, because you know that parameter R is the parameter, this is the parameter R, So I can express RA in terms of the parameter R, because this R is actually the distance of the electron from the center of mass, which is the same either the electron is connected with nucleus A or with nucleus B. In both cases, R would be the same and measured from the same center of mass. So you can replace RA and RB with R through using equation number 29 and 30. So you see that d tau E has been defined, and I have also said that the evaluation of the integrals over the electron coordinate require that both RA and RB must be measured from a common origin using a common coordinate system, which will be the center of mass coordinate system, or which will be the center of mass of the two nuclei, because the electron will not contribute much in the decision of the center of mass due to the two nuclei, which are much heavier in comparison with the electron. The potential energy curve for symmetric and antisymmetric systems are shown on the next page. Plot of kinetic energy T, potential energy EP, and the total energy E of the hydrogen singly ionized molecule are shown separately. So let's discuss the diagrams. For example, this is the diagram on the left is actually the energy of the electron in the symmetric and in the antisymmetric case. So you see that this is the potential energy curve for the symmetric and antisymmetric systems. So these are the potential energy curves for the symmetric and the antisymmetric systems. For the antisymmetric system, you can see that EA has been plotted over here. It monotonically decays with the value of R. As you increase the value of R, the function will decrease. But you know that for the symmetric case function, you can observe a dip in the function. That is, the function has a minima. It means that this function is the function that will give you a stable condition. So let me read the caption. Potential curves ES of R for symmetric charge distribution phi s absolute square and EA of R for the antisymmetric distribution in absolute square of phi A in the LCAO approximation. LCAO approximation means that when you consider them as a linear combination of atomic orbitals. And you see that here you can see for the case of ES that it has a dip, that is, and moreover that it is in the negative side. So negative sign means that it corresponds to the bound state. So a bound state is possible only for the symmetric wave function, and the symmetric plot of the potential energy is shown over here, which has a negative value. It means that it represents a stable bound state. Whereas the function represented by EA represents does not represent a stable system or a bound state because it has a positive energy. And you know that in the previous paragraph, I have also given the plot. I have also said that plot of kinetic energy T, potential energy EP, and the total energy E of the hydrogen singly ionized molecule are shown separately. So here I have plotted total kinetic energy capital T, potential energy E pot. E pot is the potential energy, and this E is the total energy of the molecule. And you know that for each curve, I have given three plots. One is the exact plot. Because you solve this equation, hydrogen singly ionized molecule can give you exact solution because it can be solved exactly using Schrödinger wave equation. So the solid line are the solutions of the Schrödinger wave equation giving you exact solution, because the analytical solution can be obtained using the Schrödinger wave equation. So these analytical solutions give you exact solutions. So the solid curves in black actually represent the solutions obtained, are the solutions which are exact solutions and obtained using the Schrödinger equation in case of T curve, in case of E curve, in case of E pot curve. And you know that there are two additional curves that I have shown. One is the red curve, which is the simple LCAO approximation. That is, you are combining the linear linear atomic orbitals in order to represent the problem. And where the coefficients are not optimized, for example, then of course you have a red curve. And you know that these red curves departs much from the black solid curve. Now I have also a curve which is shown by the dashed line. This is also a LCAO approximation in which the coefficients were optimized. And then of course you can see that the dotted lines are very close to the solid lines. That is, the dotted lines are very close to the exact solutions shown in solid black lines. So let me read the caption. Kinetic energy T, potential energy E pot, E potential, and the total energy E of the hydrogen singly ionized molecule in LCAO approximation with the optimized parameter eta of R in dash. So you see that here LCAO approximation, here I am using the term eta of R, which will be explained later, but here you only remember that this is the LCAO approximation in which the parameter eta of R has been optimized and is shown by the dashed line. Since this is due to the optimization of the parameter, it means that its solution will be very close to the exact solution given by the solid black line. And eta is equal to 1 in red. So for the red curves, I have used eta is equal to 1. I have used a fixed value of eta. And eta is equal to 1 for the red curves, which you know depart much from the solid black lines. And the exact calculations are shown in solid. AU is the arbitrary units, is atomic units shown on the vertical axis. Here I have used Haar tree, and one Haar tree is equal to 2 times the ionization energy of the hydrogen atom, which is equal to 27.2 electron volt. So I have plotted a Haar tree over here and defined Haar tree equal to 2 times the ionization energy of the hydrogen atomic hydrogen atom having a value of 27.2 electron volt. So you see that I have plotted on the vertical axis as the E energy in the arbitrary units, and on the horizontal axis I have plotted the value of R, which is the separation between the two nuclei in terms of the Bohr radius, A naught. So the next topic that I am going to discuss is the binding in the ground state of hydrogen singly ionized molecule. It can also be represented as atomic hydrogen ionized plus the hydrogen atom in a neutral. That is, this is the ionized hydrogen atom and this is the neutral hydrogen atom. The ground state wave function is phi s, which is the symmetric wave function. Symmetric wave function is the ground state wave function. E of R is equal to, that is the total energy as a function of R is equal to kinetic energy plus the potential energy. The repulsive force or energy between the two nuclei has to be considered. The repulsive force or energy between the two nuclei has to be considered. You know that since the two nuclei are present, nucleus A and nucleus B, we have to also incorporate the repulsive force or the repulsive energy between the two nuclei if we want to produce a realistic solution. The LCAO approximation in the limit that R goes to 0 gives. R goes to 0 means that the two nuclei are approaching to each other, and the separation between the two nuclei is diminishingly small. So under that condition, we can write that the limit R goes to 0, the total energy of as a function of R will be equal to constant minus 3 times EA. Without nuclear repulsion. So you see that the two nuclei are very close to each other with a separation approaching 0, and then the total energy is equal to a constant value which is minus 3 times EA. And here we have not incorporated the nuclear repulsion. This follows from the integrals. Since R goes to 0, a nucleus with the charge Ze, you know that since R goes to 0, so the two nuclei will combine to give you overall charge of Ze with Z is equal to 2 is formed. So a nucleus with charge Ze with Z is equal to 2 is formed. When the two nuclei approaches to each other, that is when R is equal to 0. The energy should be minus Z square times EA. And if you put the value of Z is equal to 2, you will get minus 4 times EA. And you know that here the values that was obtained through integrals was minus 3A, and the actual values that we approximate through numerical formulas is minus 4 times EA. Where EA is actually the energy of a single atom. Two different effects that contribute to the binding energy are given. Number one, at equilibrium distance RE, RE is the equilibrium distance. Let me show where it is. Where is the position of RE? This, where you have a minimum value in the curve. This corresponds to the value of RE. At equilibrium distance RE, the potential energy is lowest, which makes the total energy E of R to have its minimum. The electron charge distribution minus E times absolute square of phi s has its maximum in the middle between the two nuclei. You know that I have already plotted this function. So it has a maximum in the middle between the two nuclei. This pulls the two nuclei towards each other through Coulomb force between the electron and the protons. So you see that the electron will attract the two protons together, and the two protons comes very much closer to each other, and is thus responsible for keeping the two nuclei together. And here we have ignored the repulsive forces between the two nuclei. The molecular wave function phi s has a longer spatial extension than the atomic 1s orbitals. So you see that this phi s orbital, which is composed of the atomic orbitals, and the atomic orbitals are 1s orbitals due to this one, and this phi s has a longer spatial extension. The two atomic orbitals will combine and will give you phi s, which has a longer spatial extension. Due to this spatial uncertainty for the electron is increased. Due to this, the spatial uncertainty for the electron is increased, and its momentum uncertainty is therefore smaller than that of the single hydrogen atom, that is the mean kinetic energy. So you see that the uncertainty principle, in which we have delta P multiplied by delta X, is of the order of h bar. So you see that here delta X is increased, that is the spatial dimension of the wave function is increased, and of course delta P would then be increased according to uncertainty principle. When delta P will decrease, it means that the velocity of the electron will decrease. And when the velocity of the electron will decrease, it means that the mean kinetic energy of the electron will decrease. And that mean kinetic energy of the electron is given by equation number 49. That is the average kinetic energy of the electron is equal to the average value of a momentum, average value of a p square over 2m, where p is the momentum of the electron given by m times the velocity. And here you know that since the wave function in the phi s is elongated, becomes elongated, then it means that the uncertainty in delta X is increased, and the uncertainty in delta P must be decreased. So it means that the velocity in P will be decreased. This relatively improves binding energy, because the kinetic energy is decreased, the binding energy will be improved. In the LCAO approximation, the main contribution to the binding energy comes from the lowering of kinetic energy. In LCAO approximation, the main contribution to the binding energy comes from the lowering of kinetic energy. So you see that I have explained how the lowering of kinetic energy occurs in the LCAO approximation, and of course the binding energy. And in the LCAO approximation, the main contribution to the binding energy comes from the lowering of kinetic energy. So when the kinetic energy is reduced, the binding energy is improved, while the exact solution shows that the binding energy is mainly due to the decrease of potential energy. So you see that here we have established that the lowering of kinetic energy improves the binding energy under the LCAO approximation. But you know that we have also noticed that under the exact solution, the binding energy is mainly due to the decrease of potential energy. So here in the first, I have said lowering of kinetic energy, that is the decrease in kinetic energy, and following the exact solution, I have found that the decrease in potential energy is responsible for the binding energy of the system. So it means that the LCAO approximation would require improvement so that it can match the exact solution, or it can match the interpretations given by the exact solutions. Now improvements to LCAO model. We wanted to suggest some improvement, because we have seen this we have seen some discrepancy between the LCAO model, between the solution obtained from the LCAO model and between the solution obtained through exact calculations. So improvements to the LCAO model are required. To improve the LCAO approximation, the unperturbed atomic model and unperturbed atomic orbital phi A which I have already defined earlier, which is equal to phi a as a function of Ra is equal to 1 over square root of pi into a naught cube multiplied outside of this is e to the power minus Ra over R naught. So I am going to modify this one for the improvement of the LCAO model to appear as phi a is equal to c times within the parenthesis I have 1 plus lambda times z, and then I have e to the power minus eta of r multiplied by Ra over R naught. You know that this is eta of r, which I have mentioned in connection with the plots given over here. And you know that here I have talked about the optimization of the parameter eta of r. And this eta of r appears in the calculation in equation number 51. So phi of a is equal to c times 1 plus lambda times z, where you know that z is the z axis and on which the two nuclei are located, and then e to the power minus eta of r multiplied by Ra over a naught, where lambda and eta of r are optimized for each nuclear separation r to bring the energy E of r to the minimum. So you see that here the solution will be improved when E of r will have a minimum energy. And for that one, we are going to optimize the parameter lambda, and the other parameter is eta of r, so that E of r will have the minimum energy. Lambda ensures that the charge distribution of the electron Lambda ensures that the charge distribution of the electron in the force field of two protons is no longer spherically symmetric. Lambda introduces a deformation in the z direction, which reduces the spherical symmetry to cylindrical symmetry. So you see that here the important point is that it is the factor lambda that ensures that the distribution of electron is no longer spherically symmetric. So lambda introduces a deformation in the z direction of the molecular orbital, which reduces the spherical symmetry to the cylindrical symmetry. So that's why you see that in the previous lecture I introduced the cylindrical coordinate system, because we have to deal this problem in the cylindrical coordinate system, because we don't have spherically symmetric potential. We have a potential which varies, or which could have some symmetry in the cylindrical system. Absolute square of phi a and absolute square of phi b depend on the nuclear separation, which is described by eta of r. For eta greater than 1, phi a and phi b are contracted. So you see that if eta becomes greater than 1, then phi a and phi b, these are the two atomic orbitals, they will be contracted, which causes a lowering of energy, because the electron charge becomes more concentrated between the two nuclei. So when phi a and phi b are contracted, this causes a lowering of energy, because the electron charge becomes more concentrated between the two nuclei. Contraction of orbitals gives the electron less space in the x and y direction, because our atomic orbitals are contracted in the xy plane, contracted both along the x-axis, contracted both along the y-axis. And the contraction of the orbitals give electron less space in the x direction and in the y directions. This increases the mean kinetic energy due to uncertainty principle. And you know that since the delta x is reduced along the x direction, delta y is also reduced along the y direction. And you know that the uncertainty principle says that delta p into delta x is of the order of h bar. So when delta x is reduced, delta p will be increased. So it means that the kinetic energy or the mean kinetic energy will be increased in both directions. along the x direction and along the y direction. And the average value of kinetic energy in the perpendicular direction. This super sign is the perpendicular direction sign. That is, we are calculating this kinetic energy in a direction perpendicular to the z-axis. That's why we are talking Vx square and Vy square. So our average kinetic energy in a direction perpendicular to the z direction is half m average of Vx square plus Vy square as given in equation number 52. In the z direction, the molecular wave function is more expanded, leading to decrease in kinetic energy. So you see that the wave functions are reduced in dimensions along the x and y direction. And so their ultimate result is that their expansion along the z direction is decreased. So in the direction of the molecular wave function, in the z direction, the molecular wave function is more expanded, leading to decrease in kinetic energy. And since we are here giving the kinetic energy expression for in a direction parallel to z axis, so I have written average value of kinetic energy in the parallel direction, that is along the z direction, is equal to half m average value of Vz square. And you know that here we are establishing that the kinetic energy along the z direction is decreased, whereas the kinetic energy along the x and y direction are increased. A small net decrease in kinetic energy is obtained for the improved LCAO approximation. So you see that this is according to our improved LCAO method. And you know that the improved LCAO method is this given by equation number 51, whereas the simple LCAO method is given in equation number 50. The improved LCAO method gives you the equation shown in equation number 51. A small net decrease of kinetic energy is obtained for improved LCAO approximation. The decrease of kinetic energy is, however, smaller than the decrease in potential energy. So you see that here, using the improved LCAO method, we have established that there will be a decrease in kinetic energy, but at the same time, we should appreciate that the decrease in kinetic energy is smaller than the decrease in potential energy. So potential energy is more fastly will be decreasing more rapidly. Physical reasons for molecular binding. Now we shall try to establish how the molecular binding results even in the presence of the repulsive forces between the two nuclei. When the molecule is formed, the atomic orbitals are deformed. When the molecule is formed, the atomic orbitals are deformed in such a way that the decrease in potential energy E part of as a function of R at the equilibrium separation R is equal to RE, and the decrease of kinetic energy as a function of R over compensates the energy necessary for the contraction and deformation of the atomic orbitals. So let me read this paragraph once more. When the molecule is formed, the atomic orbitals are formed in such a way that the decrease in potential energy at the equilibrium separation R is equal to RE, and the decrease in kinetic energy overcompensates the energy necessary for the contraction and deformation of atomic orbitals. And you know that I have already said that this contraction and deformation of the orbitals occurs in the x and along the x and y axis. This gives the energy minimum at R is equal to RE, below the energy of the separated fragments. So you see that we have the minimum energy at R is equal to RE, which is actually the minimum energy of the separated fragments. That is, the energy will be minimum even at the energy of the individual hydrogen atom and the individual singly ionized hydrogen atom. So this energy which occurs at R is equal to RV will be minimum. The binding energy of the hydrogen singly ionized molecule is given. by equation number 54. So here EB, that is the binding energy of the molecule on the left hand side, is equal to energy, total energy of the hydrogen atom in its ground state, which is 1s. 1s is actually the ground state of the hydrogen atom, and then minus the energy, binding energy of the hydrogen molecule when it is in the 1 sigma g state at R is equal to Re. You know that I have already discussed these sigma states, that is 1 sigma g state. I have already discussed this state in the previous lecture. So when this molecule H2 singly ionized molecule is in state 1 sigma g, and its energy is at R is equal to Re is here mentioned. So we are mentioning this energy of the molecule at a fixed value of R is equal to Re. So on the right hand side we have the energy of the hydrogen atom in its ground state minus the energy of the singly ionized molecule in its ground state at R is equal to Re. The difference between these two energy states will give you the binding energy of the hydrogen singly ionized molecule. It is the difference between the electronic energies of the atomic 1s state and the molecular H2 singly ionized state at equilibrium nuclear distance R is equal to Re. So this difference of energy will provide energy for the binding of the H2 singly ionized molecule. And you know that when the H2 singly ionized molecule is formed, there are two combinations, that is the hydrogen atom should be there, and the singly ionized molecule, the energy of that molecule is also important. So we have given you the energy of the hydrogen atom in its ground state minus the energy of the hydrogen singly ionized molecule when it is in the ground state and when it is at a distance of R is equal to Re. So this difference of energy will provide you the binding energy of the hydrogen molecule. And if you roughly calculate this energy of the binding energy of the hydrogen singly ionized molecule is of the order of 1/5 the binding energy of the hydrogen atom. And you know that the binding energy of the hydrogen atom means that the binding energy of the electron in the hydrogen atom, which is nearly of 13.6 electron volt. Eb is the energy necessary to dissociate the molecule. So you see that if you want to dissociate this molecule, you need to provide this much energy, that is energy equal to 1/5 the energy required for the ionization of the hydrogen atom. So if you provide this much energy to the molecule, which is H2 singly ionized molecule, then this molecule will be dissociated. Mean kinetic energy and the potential energy of the electron in the hydrogen singly ionized molecule is E ionized. You know that is 13.6 electron volt of the hydrogen atom. This is the energy that is required to ionize a hydrogen atom. And you know that 1/5 of this energy is required to dissociate the molecule. So mean kinetic energy and the potential energy of the electron in the hydrogen molecule, hydrogen singly ionized molecule, are tabulated and presented under various methods. So you see that this energy, that is the kinetic energy and the potential energy of the electron in this molecule, that is in the hydrogen singly ionized molecule, is presented in the next page in the form of table comparing different methods. For example, in the leftmost column, I have the column with methods, which includes LCAO, hydrogen singly ionized method at R is equal to Re. And this is the second one is the LCAO method at an eta is equal to 1.25 value. The third one is the exact calculation value, and the fourth one is the hydrogen plus the singly ionized hydrogen at the approximation that R goes to infinity. That is the two atoms, that is the hydrogen atom and its ionized counterpart are farther away, much farther away from each other. So you see that I have here in the second column, I have given you the kinetic energy, which is half mv perpendicular square. V perpendicular square means that it is the kinetic energy in the x direction or in the y direction. And then I have the column with half mvz square. So this is the average value of the kinetic energy in the z direction. Then I have ek, that is the total energy, total kinetic energy of the electron. Then I have the potential energy of the electron, average value of the potential energy of the electron. And then the last most column gives you the total energy of the electron, combining both the kinetic energy and the potential energy. So here you see that the values are given. For example, for the LCAO H2 ion at R is equal to Re, you can see different values 0.6, 0.18, 0.78, minus 1.9, and minus 1.12 are given. For the LCAO eta with eta is equal to 1.25, I have the value of 1.92. That is the energy in the kinetic energy in the perpendicular direction, that is in the x and y direction, are increased. And the energy in the z direction is also increased. The kinetic energy of the electron is also increased, and the potential energy of the electron is also increased. The magnitude is increased, but of course the negative with negative sign, the value is decreased, and the total energy is minus 1.12, which is of course a negatively increased value. Exact calculation gives you 0.95, 0.30, 1.25, minus 2.5, and minus 1.25 as the total energy. Because this exact calculation will provide you a reference for the comparison of other values. So if the other values are close to this exact value, exact calculations, then of course you can assume that those values are very close. Those methods give close values to the exact calculations. Then I have this one where the hydrogen atom is the two, where the hydrogen atom and its singly ionized counterpart are much farther away from each other. And you know that the separation is also increased 0.67, 0.331, minus 2, and then minus 1.0. So here you can see that which value is closer to that one. So you can assume that the LCAO with eta is equal to 1.25 is a value that is close to the exact value. So it means that the LCAO method with the eta is equal to 1.25 gives you the results which are close to the exact calculations. And then you see that the wave functions are compared over here. Wave function phi s, that is the we are discussing the spherical, we are discussing the symmetric wave function. We are discussing the simple LCAO method, using simple LCAO method, using optimized using LCAO method with optimization and with lambda is equal to 0, with optimization of eta parameter and lambda is equal to 0. The third one is polarization included. That is, you are including the polarization effect within the molecule, which requires that eta is not equal to 0 and lambda is not equal to 0. And at the end, and the last one is the exact calculation. And in the second column, I am giving you the binding energy of the molecule in electron volt. And the third one is the value of these parameters at the value of Re, which is the equilibrium distance value in terms of the Bohr atomic radius A0. So you can see that these values, simple LCAO method gives you 1.76 and Re value is 2.5. The LCAO optimized method with the lambda is equal to 0 gives you 2.25 with the Re value equal to 2. The polarization included method gives you 2.65 with the Re value equal to 2. The exact calculation gives you 2.79 and the Re value equal to 2. So you see that you can see that the LCAO method with the eta optimized and the lambda is equal to 0 gives the value 2.25, which is closest. The polarization included method gives you the value which is closest to 2.65 is closest to 2.79, and the two for the value of R is the same as for the exact calculation. So it means that if we include the polarization is in when the polarization is included and with the parameter is eta is equal to eta not equal to 0, lambda not is equal to 0, then this method gives you the wave function which has a value very close to the exact calculations. Different steps for improving the LCAO approximations gives binding energy and the value of Re as comparative variables. So here you say you can compare different values, different LCAO methods, different values of EB and Re, which can be compared with the exact calculations of the different LCAO methods under different parameter settings. So let me first of all to explain these curves. But before that, let me read the caption of for these curves. Comparison of potential curves E of R for hydrogen singly ionized molecule for different approximations and experimental values. So you see that we are giving you a plot of the different potential curve values for the hydrogen singly ionized molecule using different approximations and also with the experimental data. The experimental data is shown in 5. The curve number 5 gives you the experimental data. So 1 gives you the result of the simple LCAO method. Simple LCAO method is given in plot number 1. And you know that plot number 1 is much deviating from the plot number 5, which is the experimental data. The second number 2 is the LCAO with the optimized parameter eta of R. So the curve number 2, which is shown in a dashed dotted line, is the curve which is obtained with the LCAO method and with the optimization of the eta of R parameter. It is relatively better than the curve given in 1, but still it is further away from the exact calculations, experimental calculations of curve number 5. Then you see that the third number curve, the third one gives you the inclusion of the polarization effects of the parameter lambda. So the third one gives you the plot where we have included the polarization effects. And you know that the curve number 3 is much better in comparison with the previous 2 curves. So this is the green curve. The 3 number curve is shown in green. The number 4 is the calculation by James and Coolidge. So James and Coolidge also carried out some calculations, and their results are shown in the curve given in equation, curve given in 4 and shown in red. So this will be discussed later on. That is the James and Coolidge contribution will be discussed later. And number 5, you know, that is the experimentally obtained data. So you can compare these results, that which one is closer to that one. So you see that the result is that the curve number 4 obtained by the James and Coolidge method is a relatively much improved version of the previous method and is very close to the experimental data given in number 5. And you know that at the bottom I have shown the binding energies. In negative, the negative one is the binding energy, which is minus 2.79 electron volt, and the positive one is the energy that is required to ionize the molecule in this state. So the LCAO results approach the exact result with the increasing number of optimized parameters. So if you include increased number of optimized parameters, then of course the results are improved. For example, James and Coolidge produced the best result by using linear combinations of 50 basis functions. That is, 50 basis functions were used by the James and Coolidge in order to obtain the curve number 4, which is much closer to that of the experimental data. With the simplest rigid molecule, H2 singly ionized molecule, more refined approximations have to be used in order to reach the accuracy of the exact calculations. As obvious from these curves, that more accuracy is required for the calculations given in number 4 to meet the experimental data given in number 5. So you see that here I have given you the second lecture on the molecular part of the atomic physics. And this lecture is continued, and so far this is the end of lecture number 18B.